All right, so we're going to continue looking at examples for solving these DEs using this undetermined coefficients approach that we've been talking about. In this example, as all of the examples will be, we're looking at linear DEs with constant coefficients, non-homogeneous. And in this case, I have a combination of a cosine and an exponential function occurring in the same function that I would normally think of as g of x. Okay, so like I said before in the previous video, there's only certain functions that we can use this approach with, certain functions for that g of x there, but you are allowed to add or multiply those functions together to create new ones that this approach still works on. So for this guy, we're going to do what we've been doing first. We find that auxiliary equation. This one is going to look like m squared plus 3m minus 10 equals 0. This guy factors nicely. We get m plus 5 times m minus 2 equals 0, which gives me m equals negative 5 and 2, giving me the following complementary solution. yc equals c1, I'm going to put the 2 first, e to the 2x plus c2 e to the negative 5x. Okay, remember that first step is always necessary to do that first. We're actually going to see in a couple of examples why it's extra important that you do that first. But that's out of the way. Let's make a guess as to our particular solution. Well, like we said in the previous example, if you have a cosine showing up here, it's not enough to just make cosine the only part of your particular solution. You need a sine and a cosine, because derivatives, successive derivatives of this function will produce both sines and cosines, depending on how many times you differentiate. So for this first function here, because I'm seeing a cosine of x here, I'm going to assume that my particular solution has an a cosine of x plus b sine of x showing up in there somewhere. Okay, I also have this exponential function, e to the 3x. So I'm also going to tack on a plus c e to the 3x. Notice I'm not using the coefficients negative 130 and 16 here. That's because these coefficients are what I'm going to be setting things equal to later solve for a, b, and c. Okay. Now what we need are some derivatives. So yp prime is negative a sine of x plus b cosine of x plus 3c e to the 3x. Yp double prime is going to equal negative a cosine of x minus b sine of x plus 9c e to the 3x. Pretty straightforward differentiating that one. Pretty painless. So what do we do now? Well, as we saw in the previous example, we have to plug all three of these guys up into this DE up here, and as expected, that gets a little bit messy. So let's go ahead and just plug it in, though. So y double prime, yp double prime is going to go in for y double prime there. That's going to give me negative a cosine of x minus b sine of x plus 9c e to the 3x. And then I have plus 3 times yp prime is what I'm plugging in there. 3 times that, negative a sine of x plus b cosine of x plus 3c e to the 3x. Okay, and then up there, that's going to go in for my y, so that's minus 10 times yp. So that's a cosine of x plus b sine of x plus c e to the 3x. That whole thing should be equal to what we have up here. Can I squeeze that in? Is that going to fit? Negative 130 cosine of x plus 16e to the 3x. I'm actually kind of proud of myself. I crammed all that into one line. Just barely, though. All right, so remember that first step where everything gets plugged in creates this beast of an equation. But then this is where you do some algebraic gymnastics, and you simplify it way down by combining sines with sines, cosines with cosines, exponentials with exponentials. And this one's pretty straightforward to do. Starting with the cosines, you can see, for example, I have a negative a cosine of x, negative 10a cosine of x. That's going to give me negative 11a. And then over here I also have 3b cosine, so I'm going to get a plus 3b showing up for my cosine of x there. Okay, and then if you do the same thing with the sines, what do we have? Negative b sine of x here. I'm going to have a negative 10b sine of x there, so that's negative 11b. I also have a negative 3a sine of x, so I'm going to have plus negative 3a minus 11b sine of x. And then let's go ahead and combine, let's combine all the exponential functions. So I have a 9 here. This 3 is going to distribute, give me another 9 there. And then I'm going to have, so that's 18. Then I'm going to subtract 10. So it's going to be plus 8c e to the 3x equals negative 130 cosine of x plus 16e to the 3x. Okay? Now remember, once you get it down to this step, right, because we have a single cosine term, a single sine term, and a single e to the 3x term. And because this is an identity, we can equate coefficients, right? So in the absence of a sine of x here means that we set this coefficient equal to 0. So really what we have here is negative 11a plus 3b, which is the coefficient of my cosine, equals negative 130. And then I have negative 3a minus 11b equals 0, right? I'll deal with the c next, and that's the easiest one to deal with. Again, I'm not going to go through the steps of solving this system of equations because it's straightforward. It's not a complicated one to do. It's just a little bit of work that I don't want to waste time on. But what we end up getting for this is a equals 11 and b equals negative 3. Okay? Next step, I want to solve for c. So again, I would set 8c equal to 16. 8c equals 16 implies that c equals 2. So there's my coefficients. A equals 11, b equals negative 3, c equals 2. I could write y of p equals this thing with those coefficients plugged in, but why not just jump straight to the answer? So y equals our complementary solution, which you can see up there, c1 e to the 2x plus c2 e to the negative 5x plus our particular solution plus 11 cosine of x minus 3 sine of x plus 2 e to the 3x. Those are the coefficients that we found. There we go. General solution. Okay? Not too bad. Not too bad. But again, just some tedious algebra. At this point in your mathematical career, it's nothing you haven't really seen before as far as algebra goes. Let's try another one. This time, instead of a sum of two different types of functions, so cosine plus, a cosine plus an exponential function, we're going to be dealing with a product of two of those types of functions, an exponential times a linear combination of cosine and sine. Okay, so let's set up our auxiliary equation first, as we always do. Auxiliary equation in this case is going to look like m squared minus 2m plus 2 equals 0. It doesn't take much time to determine that this guy does not factor, which means we would have to use the quadratic formula to solve it. I'll let you do the quadratic formula, but this one ends up having complex solutions. We end up with m equals 1 plus or minus I. Okay? Again, you do the quadratic formula. I know you know how to do it. This gives me a complementary solution. Remember, this is case 3 from section 4.3. How do we use these guys, this 1 and the 1 in front of that I right there? Well, my complementary solution in this case is going to look like C1 e to the x cosine of x plus C2 e to the x sine of x. Okay, that would be my complementary solution. Now, we have to guess what our yp is going to look like. And looking at the form of this, it kind of makes sense to assume that our yp is going to look like an exponential function like this one times a linear combination of sine and cosine. So I'm going to make this as my guess. Yp equals a e to the 2x times b cosine of x plus c sine of x. And here is where we get to really messy calculus, which I am not going to spend a bunch of time doing. So notice, in order to do the derivatives, we need two derivatives here, because we go up to y double prime. We're using the product rule, right? But once you've used the product rule, you then have to simplify by combining like terms. I am going to jump straight to what would happen if you did the product rule, combined all the like terms, and got this thing looking exactly how we want it to look. The derivative will look like this: a e to the 2x times 2b plus c cosine of x plus negative b plus 2c sine of x. Okay, and just double check my notes to make sure I did not write anything down wrong, but that looks correct. Okay, now I need y double prime, or yp double prime. And again, this would require the product rule, and I would have a lot of combining of like terms to do. I am going to jump straight to what that would look like after doing the simplification. So this is going to be 3b plus 4c cosine of x plus negative 4b plus 3c sine of x. Please don't just take my word for it. I know that's easy to do, but check, you know, I mean, because you're going to be doing this in the homework anyways, you are going to have to fill in those gaps. So why not get the practice now? You know, make sure that this is what the derivative of this thing would look like after doing all the simplifying. And then same thing here, you know. Let's take all of this and put it into my differential equation up here. Now I want to make note of something. All of these functions here, yp, yp prime, and yp double prime, look like a linear combination of cosines and sines times the exact same factor out here, a e to the 2x, a e to the 2x, a e to the 2x. If I plug all three of these guys into this dE, then each of these terms will have that same factor, a e to the 2x, which I can then just factor out completely. So I'm going to do that ahead of time to save on a little bit of space. A e to the 2x. It's going to be pulled all the way out. Now let's look at what we have left. So I have y double prime. Okay, that's this guy with the a e to the 2x pulled out. 3b plus 4c cosine of x plus negative 4b plus 3c sine of x. Okay, next we have minus 2 times y prime, or yp prime in this case. That negative 2 is going to be multiplied into these square brackets here, because remember, we're taking the a e to the 2x out. If I multiply the negative 2 in, I'm going to go a little bit further and bring it into each of these smaller sets of parentheses here. So now I'm going to have negative 4b minus 2c. See how that works? Cosine of x. And then again, multiply a negative 2 into here. That's going to be plus 2b minus 4c sine of x. Okay? And then I have one more to go. Notice I'm not going to be able to fit the whole thing on one line here. Plus 2y, that's 2 times this guy. Well, that 2 is going to distribute into both of these terms, so I'm going to get plus 2b cosine of x plus 2c sine of x. Now that is the entire left-hand side, but my right-hand side I ran out of space for, so I'm going to go like this. That equals e to the 2x times cosine of x minus 3 sine of x. Okay? Lots of combining to do here. Combine all 3 of these cosines here, all 3 of these sines here. What's that going to give you? A e to the 2x times, when we simplify this down, it's going to look like b plus 2c cosine of x plus negative 2b plus c sine of x equals e to the 2x times cosine of x minus 3 sine of x. That looks a whole lot nicer than that, right? And I like being able to just sort of snap my fingers and say, look, we went from here to here without having to do all the work that, sorry, but you're going to have to do. So now what do? Well, we equate coefficients. Remember, that's how we solve for a, b, and c. So what's the coefficient on my e to the 2x here? It's 1. Therefore, that a is equal to 1, right? Now we equate coefficients here. This time I have both a cosine and a sine on the right-hand side. So now I don't get to set anything equal to 0. I'm going to set this guy equal to the coefficient on that cosine, which is a 1. b plus 2c equals 1. And then this guy, negative 2b plus c, that gets set equal to negative 3. Again, system of 2 equations in 2 variables. This one is not complicated to solve. We're going to end up with b equals 7/5 and c equals negative 1/5. Okay? It's not magic that I'm getting that. I did the work ahead of time. Okay? You'll have to go through the work. If you did this problem on homework, it would take more space because you're going to be showing more work here than I am. Putting all this together, we can get our general solution. Y equals our complementary solution, which was up here, c1 e to the x cosine of x plus c2 e to the x sine of x plus our complementary solution, which is that guy after we plug in the coefficients we just found. So that's going to look like plus, a was 1, so that's just e to the 2x, times b cosine, so b was 7/5, minus 1/5 sine of x. That's our solution. Okay? Not too bad. Not too bad. You're probably thinking, what do you mean not too bad? That was a lot. So this table I copied out of your book, and it's basically just a breakdown of which types of functions lead to which kinds of guesses for your particular solution yp. It's kind of just following the same intuition that we did. These are all examples. So, this is an example of a linear function. If you have 5x plus 7 as your g of x, you would then guess ax plus b. You would guess a polynomial of the same degree, but with general coefficients. Notice here, for example, if I have x cubed minus x plus 1, this is a cubic polynomial. Notice that even though it's missing an x squared term, your guess for y of p should include an x squared term. All that means is that once you get to that final step where you're equating coefficients, whatever the coefficient on your x squared term looks like on the left-hand side, you would just be setting that equal to 0, because that's the coefficient of the x squared on this side. In fact, the same thing holds even if I was just trying to... actually, let me use this as an example. So here we have a product, x squared times e to the 5x. That x squared, as innocent looking as it is, the yp is going to include a general quadratic an entire quadratic, ax squared plus bx plus c, even though we only have an x squared over here. Because that is an x squared term, we need an x squared term in all terms with lower degree than that as well. So use this as kind of a guide to guessing, what y of p should look like. But given the, what was it, 4 examples that we've done between the first 2 videos here, you should have a kind of a general idea of how this works. Now we're going to save this for the 3rd video, but the next example that we're going to do, we're going to try and follow the same guidelines, and we're going to see that our initial guess messes things up. So I'll explain what I mean by that in the 3rd video.